Hello, we are now going to talk about the first part of chapter 7.6.2. So this would be actually part 1, which is the main part we're going to be doing with the one sample sampling distributions. And in the second part of chapter 7.6.2, we're going to be dealing with when we do with a difference of two proportions. So this is just in essence with one proportion. But so what is a sampling distribution of a sample proportion? We talked about this in chapter 7, section 1. What it is every value that a sample proportion, in other words, a p hat, can take in repeated sampling. If we were to take many samples, is every value, the sample statistic, which is a proportion in this case, can take in repeated sampling. So what's happening is we've got some population proportion. So let's say, for instance, we've got our population is all the dogs in Alabama, let's pretend. And so we're interested in the proportion that are beagles. And let's pretend that is like 12.1%. So 12.1%, which would be 0.121. Okay, but we don't know that, so we're estimating it. So the population parameter is 0.121, but we take a sample. All right, so let's say if we take a sample of 100 dogs, our sample size is 100 dogs, and we find that 10 of them are beagles. And so our statistic, our p hat sub 1, is 10 divided by 100, which is 0.1. And so there is our first p hat right there. The concept of a sampling distribution, what if we took another sample and got another p hat? Well, it's almost certainly going to vary from this. Maybe on the next one, we get like 13%. And the next one, we get like 12%, and so forth. And if we took many samples, as was explained in section 7.1, and found many sample proportions, this family of p hats, all the possible values of p hats, if we took many samples, this is what we call a sampling distribution. That is the sampling distribution of a sample proportion. It is every value the sample proportion could take in repeated sampling. And by the way, so what we're going to talk about in this section, how does this look like it varies? Well, there's a good chance if our sample size is big enough, all right, if it follows the specifications that we're going to talk about, it'll be approximately normal, and we'll be able to do normal calculations with it, which is sort of the heart of the chapter. All right, so the distribution of sample proportions can be described by its center. Now, the center of the p hats, as long as we don't have any sort of bias, it's going to be centered at p, the true population proportion. So our little notation for that, the mean of all those possible values of p hats is in fact equal to the population proportion. And that is the first little formula on your formula sheet in regards to sampling distributions. So we have sampling distributions and inferential statistics on the second page of your formula sheet. And then so for one population, the mean for a proportion, the mean of the p hats is equal to p. Okay, so there you go. And so now, so what about its spread, its standard deviation? Well, you may have just noticed there, the standard deviation follows this formula. And we could actually derive this formula using the binomial formula for standard deviation, because in essence, dividing by n, we're taking a mean or an average. So, but anyway, but you just have to know the formulas on your formula sheet. And so it's the square root of p times 1 minus p over n. So this would be sigma of the p hats. Okay, the standard deviation of these p hats would be the square root of p times 1 minus p over n. So that's the standard deviation. Now, an important thing to know, both those things are on your formula sheet. When can you use this formula? And that's as long as the sample size isn't more than 10% of your population. So the sample size cannot be more than 10% of the population. Okay, so in this one up here, the example I was using up here, we took a sample of size 100. The population size has to be at least 1,000, or our notation is that our sample size has to be less than or equal to 0.1 times our population size, little n sample size, big N population size. And so the reason for that, if your population is too small, and we in essence basically always use sampling, most of the time use sampling without replacement. And so every time you're taking someone out of or something out of the population, you're slightly changing the population. All right. But as long as your population is big enough, it won't make a significant difference. And that's our rule of thumb. This is not some mathematically proven thing. It's a rule of thumb. So that is something important to memorize right there. It's one of our conditions to getting accurate data is our population size. The other way of wording this, by the way, is the population size has to be at least 10 times the sample size. But so that's what we call our 10% condition. Its shape. All right. Well, the shape of the p-hats will be approximately normal if something is true. And so here's our little rule that you have to memorize. Approximately normal if n times p and n times 1 minus p are greater than or equal to 10. You have to memorize that, okay? Now, if one, and both of them have to be bigger than 10. If one of them is less than 10, then it's going to be some other shape, which we'll talk about later in the year. But that's the other condition that you have to check. And because if those things are true, then we can use our normal functions, normal, CDF, inverse norm, to solve problems. So those are our two rules you have to memorize right there. So that's important. Approximately normal, n times p and n times 1 minus p are greater than or equal to 10. There's a different rule for means, by the way. So going back to this, it says when you're describing a distribution, you would cuss, okay? And so what you would say is well, this would take care of the center, is the mean is that, and that would take care of the spread, and its shape's approximately normal. And by saying it's approximately normal, that takes care of its unusual values as well. That describes the nature of its of its outliers. And so there we go. All right, certainly the best way to understand this is I think looking at examples. So let's look at this one right here. So this one says 58% of people in a city own a car. A sample of size 200 is taken of all the people in the city, and the portion that own a car is noted. Draw a sketch of the sampling distribution of the sample portion and describe it. So here's our P. Our population is all the people in the city, and our parameter is a proportion 0.58. Okay, that is not a p-hat. That's not a sample value. It doesn't say 58% of the sample. Okay, it says 58% of all the people, so it's a p. If it was 58% of the sample, that would be a p-hat. Okay, so our sampling distribution is, okay, so draw a sketch. Our sampling distribution is every value p-hat could possibly take. And so it's going to be centered at 0.58, all of these p-hats, assuming I haven't done anything in any sort of a biased way. So the sampling distribution is every value p-hat could take in repeated samples of the same size from the same population. So all these p-hats come from repeated sampling. If we took many samples of size 200, okay? So we will say this. All right, so our shape will be approximately normal. Now let's do our little test for that. N times p. So we got to test the n times p and n times 1 minus p. Both have to be greater than or equal to 10. And so this would be our n is still be 200 times 0.58, and that's 116. And so then we have 200 times 1 minus that, which would be 0.42, and that'd be 84. They're both greater than or equal to 10. So yes, it's approximately normal. Okay, so it's going to be approximately normal. That would take care of the shape and the outliers. The mean is equal. The mean of the p-hats is equal to p, and that's equal to 0.58. And then the standard deviation, the sigma, is going to be equal to the square root of p times 1 minus p over n. So that's 0.58 times 0.42 over 200. And when you do that, I believe you get 0.0349, like that. And so there we go. And so we're asked to describe it. So you would just write a little paragraph saying, well, it's approximately normal with that mean and that standard deviation, and that would take care of your cussing. All right, so then the next question is this. What values of the sample proportion would cause you to doubt the 58% figure? All right, And in general, our rule of thumb there, if it's beyond 2 or 3 standard deviations from the mean, we say it's an unusual value. Okay, it's an unusual value. So if we look at this curve, let's look at where our standard deviations are going to be. So there's right in the middle is 0.58. Halfway down this hill is 1 standard deviation. Of course, we had that in chapter 2. So if I go up 0.0349, that would put me to 0.6149. And if I go up 2 standard deviations to there, that's going to take me to 0.6498. I just added another standard deviation, so 0.6149 plus 0.0349 to get that. And if I go down 1 standard deviation, be halfway down this hill there, so I'd go 0.58 minus 0.0349, and so that's going to be 0.5451, like that. And if I go down 2 standard deviations, if I subtract 0.0349 from 0.5451, that would take me to 0.5102. Anything outside of 2 standard deviations is a good rule of thumb for us, is going to be unusual and is going to cause us to doubt 0.58. Now, we're going to be a little bit more exact about that later in the year. So what will cause you to doubt the figure? What values of the sample portion? If our p hat is greater than 0.6498, or if our p hat is less than 0.5102, that is above 2 standard deviations above the mean and below 2 standard deviations below the mean. Those would be unusual values to us that would cause us to doubt the validity of the 58% figure. So anyway, so there you go. Okay, example 2. It is claimed that a company delivers its packages 80% of the time. You take an SRS of 50 deliveries and find that 38 of them, 76%, were on time. If the 80% figure is correct, what's the probability that you get a sample portion as low as 38 out of 50 or lower just by sampling variability? Does this give us reason to doubt the 80% claim? So this is the reasoning of a hypothesis test we're going to do in future chapters, is we're sort of testing this 80% figure. So we're suspicious that maybe they aren't on time as much as they claim. And so we get a sample value that's lower. But the real question we're asking here, is it statistically significantly lower? In other words, is it plausible that that difference is due to sampling variability, just to random chance? Or is it so far below it that it would cause us to doubt the 80% figure? So, and so what we've got here, is we need to think about our sampling distribution of our p hat. So it's assuming the 80% figure is correct. So if the 80% figure is true, here's what our sampling distribution looks like. It would be normal. Okay, centered at 0.8. Now, by the way, why is it normal? The reason it is normal is because n times p, which would be 50 times 0.8, and 50 times 0.2, n times p and n times 1 minus p. So that would be 50 times 0.8 is 40, and 50 times 0.2 is 10. Both those are greater than or equal to 10, so it is approximately normal. Okay, so we have that. All right, and so in our standard deviation here, is going to be the square root of 0.8 times 0.2 over 50. So there's our standard deviation, and so that's going to be 0.056569. Okay, so there's our standard deviation. So so what's the probability that we're going to get 0.76 or less? So our p hat is 0.76. 38 divided by 50. So what's the probability that we are going to get that or less? And so the function that's going to tell us that is normal CDF. And so to do this problem, we shall say normal CDF from negative infinity to 0.76. Our mean is 80, and our standard deviation be the square root of 0.8 times 0.2 over 50. Of course, label this as lower bound, upper bound, mu, and sigma, like that. And so technically this would be the mu of the p hats and the sigma of the p hats if you want to be really accurate. And so let's go back to our old friend, normal CDF. And so here we go. We take our calculator. So you remember normal CDF is right there in the distribution menu, right above the VARs button. So if we go second VARs, go to distribution, So negative infinity is just that. And if it didn't say that, just hit the negative key, please, not the minus sign, the negative key. So I just go negative and then just 9 billion or something like that. And then we are going 30. So this would be 0.76 or 38 over 50, which is 0.76. And then, so our mean is 0.8, not 80. Our mean is 0.8 right there. So sorry, I didn't mean to say 80, 80%, 0.8. So, so that's 0.8, and there's our standard deviation. The square root of 0.8 times 0.2 divided by 50, like that. So that's how you enter it. And some calculators will immediately take you to this screen. So you just enter those numbers, separated by commas. And so we get that this is 0.23975. So what this is telling us, assuming this 80% figure is correct, the probability we would get 76% or below is about 24%. And so what that's telling us is it's not unusual. Does this give us reason to doubt the claim? And we would say no, because 0.23975 is greater than 0.05. And that is our rule of thumb for a large or a small p-value, as we're going to call it. If you get this result that's above 0.05, you would say this result's plausible due to sampling variability. If it was below 0.05, then you would say we have reason to doubt this figure. Okay. All right. So anyway, let's look at this. So how low does a conditional probability like this, which we call a p-value, how low does it need to be for you to be seriously skeptical of the claim condition? It needs to be below 0.05. That is our rule of thumb, okay? Sometimes we're going to set it at 0.01. But in these problems, when you do normal CDF in this chapter, if you get something below 0.05, you're going to say, we've got reason to doubt whatever's claimed in the problem. Okay. If it's above 0.05, you say we cannot doubt what's in this problem. It's plausible that this difference is due to sampling variability. Okay. So let's look at this. Instead of a sample of size 50 deliveries, all right, you decide to take a sample of 500 deliveries. You've increased your sample size times 10. You find that 380 of them, still 56%, were on time. If the 80% figure is true, what is the probability you get a sample portion as low as that or lower by sampling variability? All right, so if the claim is true, this is what our sampling distribution looks like. It'll be centered at 0.8, just like it was before. Okay, now 0.76 is somewhere down here. Okay, it's somewhere down here, like that. Okay, and so we want to know this probability that it's lower than that. Well, by having the bigger sample size, it's going to change our standard deviation, by the way. But how do we find this area? How do we find this probability that it'll be as lower than that value? Well, that's normal CDF again. Normal CDF. The shaded area goes from negative infinity to 0.76. Our mean is 0.8. And our standard deviation is the square root of 0.8 times 0.2. Over 500, it's a considerably smaller value than it was before. That's the only difference in this problem is the sample size. So let's see what answer we get. And so we'll go second distribution, normal CDF, like that, negative infinity, and that's still going to be 0.76. I mean, it's 380 divided by 500, which is still going to be the same number. And then 0.8, and then this is the same thing, but now it's divided by 500. Like that. Now it's divided by 500. And so what happens is, look at how the p-value went down. Okay, so now it is equal to 0.012674. That is certainly below 0.05. Okay, so what has happened by changing the sample size? You've got considerably less variability in this curve. Okay, so values away from the mean are a lot less likely to happen. In other words, in this sample, the probability, assuming 80% is true, the probability that you would have 76% on-time deliveries or less only happens about 1.3% of the time. And that is below our 5% standard. Okay. Does this give you reason to doubt the claim? You would say yes, because 0.012674 is less than 0.05. That's what you would say. In other words, it is really unlikely to occur just by sampling variability. And so, once again, this number right here, this probability that we are finding is what we call a p-value, okay? And it is the probability that you get a sample value this unusual, as unusual as 76%, given the fact that 80% is true. All right, so why does the conclusion from the sample size 500 differ from the conclusion of the sample size 50, even though the sample proportions are exactly the same? They both had 0.76. The reason is this: the larger sample size creates less variability in the sampling distribution. The smaller, so that would be the sample size of 500. So n is equal to 500. So when our n is equal to 50, the smaller sample size, sample size creates more variability in the sampling distribution. So if you were to look at those normal curves, like when our n is equal to 50, that normal curve, it's centered at 0.8, but it's going to be, let's say it's going to be something like this. It'll be approximately normal. It'll be something like that. When our n is equal to 500, what that does to your sampling distribution, it's still centered at 0.8 because we haven't done anything biased. But now it's going to be a lot higher in the middle and a lot lower on the tails. So like, let's say 0.76 was right here. Let's say that's 0.76. So in this curve, the probability to get 0.76 is pretty likely 23% of the time. But in this curve, the likelihood to get 0.76 is only about, 1.3%. So when you have a bigger sample size, there's less variability. It makes your normal curve shrink and get higher, is what happens. And that's an important concept. The bigger sample size means less variability. Okay, let's look at this example. So this says a potato chip factory receives a truckload of potatoes each week. If they have statistically significant evidence at alpha is equal to 0.05. Now what that is telling us, as we've talked about up here, that alpha value, if our result, our p-value is below the alpha, that's causing us to doubt the claim, or as we're going to say later in the year, to reject the null hypothesis. But anyway, so is there statistically significant evidence that at least 20% are rotten? They will reject the entire truckload. One week, a truckload comes in and they take an SRS of 150 potatoes. Of those 150 potatoes, 40 are found to be rotten. If in fact the 20% of all the potatoes in the truck are rotten, what is the probability you get a sample proportion as large as 40 out of 150 or larger just by sampling variability? Okay, do you think they should reject the truckload? So what we've got here, let's assume this 20% figure is right. So that is an acceptable amount of rottenness to them. So I'll be 0.2, I'll convert it into a proportion. And so it will vary approximately normally. Why? The reason it is approximately normal is because our n times p, so that would be 150 times 0.2, and then 150 times 0.8 are both bigger than 10. So that times 0.2 is going to be 30, and that times 0.2 is going to be 120, I do believe. They're both larger than 10. So therefore, we have normality. So that means we can use normal CDF or inverse norm if we need it. And so there is all the possible values of p hat whenever we take a sample. And so our specific p hat that we get is 40 out of 150. And if our p hat, and so that in fact is equal to 0.26 repeating. So 0.26 repeating is up here somewhere. So there's 0.26 repeating. So we're asking, assuming this is the true sampling distribution, what's the probability that we would get a value here or larger? You get a sample portion as large as that or larger just by sampling variability. And if this is below 0.05, it would cause us, in essence, to reject the whole truckload. So we shall use normal CDF. Normal CDF from 0.26 repeating to infinity. Our mean is 0.2, and our standard deviation is the square root of 0.2 times 0.8 over 150, like that. So label this as our lower bound, label this as our upper bound, label that as the mean of our p hats, and there's the sigma of our p hats, right, like that. And so here we go. And so we shall say second distribution, normal CDF, and I'll go ahead and enter that fraction. What the heck, it's 140 out of 150. So 140 divided by, no, it's not 140, it's 40. 40 out of 150. So we'll do 40 divided by 150, which is 0.2 repeating to infinity. So just put like 9 billion. You could technically put 1 there because a proportion can't be bigger than 1, but anyway. And so then this would be 0.2. And so this would be the square root of 0.2 times 0.8 divided by 150, right, like that. There you go. That's how you do that. And so you hit enter. And so we get 0.02061. 0.02061. That is our probability. And that is a low probability. It is. So what we're saying is this is unlikely to happen. And we have reason to doubt that 20% are rotten. It appears from our sample that more than 20% are rotten. And it's not really plausible that this difference between 0.2 and 0.26 repeating in this curve is due to sampling variability. And so, do you think we should reject the truckload? Well, 0.0206 repeating, that is less than 0.05. So thus, our p hat, 40 out of 150, is unlikely to occur just by sampling variability. Sampling variability, assuming that P really is 0.2. Thus, we should reject the truckload. Thus, we should reject the truckload. And that's it. That is the first, that is part 1. That is most of section 7.2. And if you have any questions about that, please send them to me. And there will of course be a chapter 7, section 2, part 2 video that you can now look at. So hope you have a great day.